Hey everyone, I'm Anish and welcome back to PrepFusion. So again, we're starting with a new lecture of Bode plots. This is the lecture 7. So in the previous lecture, we learned like the type of questions which mainly comes in gate examination, how to recover the transfer function from a Bode plot. If the Bode plot is given, how to recover the transfer function. We did many questions. We learned about the conversions from decade scale to octave scales on all those different things. Have you understood it? If you haven't, then I would highly recommend you to just put the video in repeat where I was solving the questions, okay? Because I was solving it very slow and all the concepts I was explaining it them very clearly, okay? So now in this lecture what we'll do a lot of things. Three small topics we'll cover. First, we'll cover the error in asymptotic Bode magnitude plot. So what is the error between the actual plot and the asymptotic plot? Because here in Bode plot, as I mentioned earlier, right, we approximate it. I've already given you the what the error is, like we get some error. Now we will write this formally and more structured manner exactly what is the error. So question may come that can you tell me the error at the corner frequency due to this Bode plot and the actual magnitude plot, okay? That may come. What is the second topic? Second topic is analysis of relative stability parameters from Bode plots. So we have to analyze, like already have done this a few times because we have calculated omega gc sometimes. So it is very easy, not that difficult. These are only simple topics because you already know this. You already know the concept. What is omega gc? What is phase margin? What is gain margin? All these things we already know. Just have to put those concepts in the Bode plots. We'll just do one example problem which has come in the gate, and from that totally we'll understand the concept of omega gc and phase matching, all those things. Then analysis of steady state error from asymptotic magnitude plot. Okay, this one also will do. What people do and I also have to do is teach you the different relative stability coefficients, the position uh, position coefficient, the acceleration error coefficient, and the velocity error coefficient. These three coefficients. But to be honest, what you can do is simply solve it with the basics. You don't need to remember these three coefficients. Just solve the using the basic of the meaning of the steady state error, and you will get to your answer. Don't need to remember all this. So I will solve using the both methods, obviously, because sometimes question may also ask, can you tell me the velocity error coefficient of this transfer function or from this Bode plot? Then obviously you have to find the velocity error coefficient. Okay, but to find the steady state error, you don't need to remember anything. You just can use a simple formula. As we will be using simple unity feedback system, then simply what will be the error formula? Error formula will be E of t will be equals to C of t, R of t minus C of t, and steady state simply S as like limit s tends to 0 as s into E of s equals to s into R of s in brackets 1 minus transfer function. Simple that formula, okay? Very simple only. You can further reduce it to R of s by G of s into R of s by G of s. That also you can reduce, okay? So for a unity feedback system, I'm talking about for a unity negative feedback system, okay? These three things we'll do. So let's start with error in magnitude at corner frequency. So error we like error can be anywhere, okay? Error can be anywhere obviously, but mainly we're concerned at corner frequency because in the key points of Bode plots, I've already told you that the maximum error that I get is at the corner frequency itself. At the corner frequency itself. Just wait a second, let me check if this is recording. Yeah, everything is recording, fine. So maximum error we get at corner frequency. So we'll calculate what is the error. I have already calculated it previously, I think, but still we'll calculate it again. So what is the definition of error? Error in dBs at corner frequency is equals to actual value of that magnitude of the transfer function minus the approximate value of this magnitude at the same frequency, at the same corner frequency. Now for n real repeated poles, can we deduce the formula of error? Okay, no need to remember anything. From basics we can understand, okay? But I have to obviously get to a conclusion, that's why I will write down the formula, but you don't need to remember. If you understand the concept, then obviously the formula will automatically come up. So let me take a transfer function, okay, G of s, which is equals to k by 1 plus s tau to the power n, as we have n real repeated poles, okay? As well, and because like if you have single pole, what was the error? If you remember correctly, if you had single pole, the like if you had pole, the error was minus 3 dB, if you remember correctly, okay? Here I have 1 plus s tau to the power n, okay? So at the same corner frequency. Now what is the magnitude in dBs? What is the magnitude in dBs? Because mainly we are concerned in dB scale. G of j omega simply equals to, let me write this down here. 20 log k minus 20 n log 1 plus not yeah, under root 1 plus omega square. This comes up, right? So just n comes outside, n comes outside, n comes outside. So yeah, this is the basically the equation of the magnitude. Here, as we see that we are getting a slope of minus 20, and that all these things we already know. All these things we already know. So now, what is the actual value of the magnitude? So what is the actual value of the magnitude at omega equals to 1 by tau? So 1 by tau is the corner frequency here. 1 by tau is the corner frequency here. So if 1 by tau is the corner frequency here, what does it mean? So actual value. So we'll write actual value. I'll just copy this one. What is it? You simply put here omega equals to 1 by tau. What do you see? So this becomes 1 square plus 1, this becomes under root 2. So minus 20 log n under root 2. Okay. So this half can come outside. So 10 n log 2. What is log base 10 to? It is 0.3. I've told you, right, to remember that one. 0.3. It's very important. Log base 10 to 2. So 0.3 times 10 is minus 10 n. So here, what do I get? This is 20 log k minus 10 n. Okay, I hope you understand. So just I will write one thing, else again you will get confused, that this is minus 20 n, this is log base 10, this is under 2. Okay, this is under 2, and this half comes here, and this is times 3. So this is 0.3 into 20 log, this is also base 10. So if I ever don't write the base, right, it is 10. If I write ln, then it means the base is exponential, e, base is e. It is known as natural logarithm. Here this is known as log base 10. So this becomes log base 10 k minus 3n. Okay, so this is my actual value. Now what is my approximate value? So what is my approximate value? What is my approximate value? So my approximate value is simply equals to only this 20 log base 10 k. Why? Because after the corner frequency, obviously the slope changes. If you remember correctly, recall correctly, let's draw the Bode plot of this one. What is the Bode plot? So if you recall correctly, this is omega, and this is magnitude of g of j omega in dBs, and the scale is in log scale. Do remember. Okay, so what we should do? We used to approximate, right? So if omega is much less than 1 by tau, obviously this becomes much less than 1. Hence omega tau becomes much less than 1. Hence this square becomes much less than 1. Hence we can ignore this. So this becomes only 1. So log base 10 1 is 0. So only we are remained with this one. I hope you remember. Then at corner frequency, suddenly the slope changes to minus 20n. So this is how we do. And we start, let's say we start from 0.01, or you can start from 0.1 also, and at 1 by tau, you can name this as 0.1 by tau. At 1 by tau, what is happening? Certainly our slope is changing. Okay, the slope here is what? Minus 20n dB per decade. Like this is like cakewalk right now for us, cakewalk. So minus 20n dB per decade. So this is 0 dB per decade. Okay, So now what is happening? Now here what is my magnitude? My magnitude here is 20 log k, because this is tending to 0, so only I remained with this 20 log base 10 k. Okay, the magnitude is 20 log base k for the approximate value. So like this is already, we have done this, still I am revising you guys all these things. So this is 20 log base 10 k. Okay, so here the approximate value is 20 log base 10 k. Now, like, what is the error? Error formula was actual minus approximate. Actual minus approximate. Now, if we subtract these two, what do we get? So, error at omega equals to omega corner frequency is simply minus 3n dBs. This is only remaining. So, it is simply minus 3n dBs. Okay. So, yeah, this is this case. So yeah, now like you can understand that what is happening. What is my actual plot? My actual plot was something like this, because at starting it was, yeah, it was 20 log k. It was like the value was k at starting at s equals to 0. That is the decision, right? It was k, like actual value I'm talking about. You put s equals to 0 here, the value is k only. Okay, so these two are matching here. Initially the error is 0, then suddenly it is decreasing, but still here this is not decreasing. The slope is 0 here. So error is increasing, error is increasing. Then what happens? Okay, let me draw this correctly. Sorry. Error is increasing, error is increasing. Then we reach the corner point, corner frequency point. So if we reach the corner frequency point, what happens here? If we reach the corner frequency point, then the slope suddenly changes to minus 20 dB per decade. And obviously this was already reducing, and slope suddenly changes to minus 20 dB per decade. Actually, I need to draw it like this to visually more show you correctly. So this also decreases and this also decreases. So what happens is they two try to meet each other at omega infinity. Try to meet each other. Obviously the error becomes again 0. Starting error was 0, ending error was 0. At the middle error is maximum. Okay. So error function, I have already plotted it. It was something like this. Something like this. So it is obviously even symmetry. Even symmetry. Okay. Error function in magnitude scale is even symmetric. Now can we just approximate the error for phase, and approximate the error for phase? So for phase, what is happening? For phase, if you want to draw, we have already done this actually, but still let's do this again. G of j omega, it is simply for phase. Initially it is 0, so let's start from 0.1 itself. Initially it is 0. Okay, let's not start from 0.1 because 10 times before redundance after that slope comes. So let's start from 0.01 by tau. We start from here. Now what is happening? Obviously it is 0 degrees initially. Okay, then 10 times before 1 by tau, the corner frequency, what happens? Slope becomes minus 45 degree per decade, and 10 times after this, slope becomes minus 45 degree per decade. This is 1 by tau. This is 10 by tau. This is 0.1 by tau. Okay, so this is minus 45, and if you put this expression, so let's just put this expression here. So here what is the slope? Actually this is not minus 45 degree per decade. It is actually, what is the slope? Minus 45 times n degree per decade, because what does the formula become? It becomes n tan inverse omega tau. So what does this angle equation become? Angle equation, angle of j omega becomes, just simply you put the angles like the n terms are getting added each other, like For one pole, what was the tan inverse formula? Tan inverse omega tau. For two poles, it will be tan inverse minus tan inverse omega tau minus tan inverse omega tau. Another one gets added. So obviously, 2 tan inverse omega tau minus 2 tan inverse omega tau. For n poles, it will be minus n tan inverse omega tau. Okay, so it is minus n tan inverse omega tau. So this becomes minus n tan inverse omega tau. Now what is happening here? Now what is happening? Now obviously this slope is minus 45 n degree per decade. This already I have taught you. Not going to explain you again. So here what does the angle become? So obviously what is this slope telling us? If I travel one decade, my angle will reduce by 45 degree n. 45 degree n. So this is not 45. Single pole it will be 45 for a single pole. For multiple poles, n poles, it will be 45 n. Okay. And how will my phase plot look like? So phase plot will look something like this. Phase plot will be like, if I approximate it, okay, it will be something like this. Okay. So obviously what you say, around here it is even symmetric, because here error is negative, here error is positive. Okay, because it is actual minus the the approximated one. So here, like, this is the approximate, this is actual. So actual is less than the approximate one. So obviously it will start reducing, right? So this is not per se exact phase plot I'm plotting, just approximate one I'm plotting. So here error is negative, here error is positive. That's why in the key points I told that my error in phase plot will be odd symmetric. Like here also in the key point will come, it will be odd symmetric. You just plot it and you will see odd symmetric. But at the corner frequency, what is the error? At the corner frequency, I see my error as 0. For single pole, we have already done this concept. At the corner frequency, let's calculate the approximate value and the actual value. At the corner frequency, what is my value of my phase of the approximate Bode phase plot? The value of my phase is minus 45 degree n. Here what is the value? So let's put the actual here. Let me copy. Where is it gone? Okay, sorry, this is okay, this is here. So the actual value of angle of g omega. Not the magnitude, the angle. The actual value of angle of g omega, what is it? Simply at corner frequency, this is, so I should write this as at corner frequency. Actually forgot to write this there that time. 1 by tau. Okay, so this is also at corner frequency. Okay, so actual value of angle of g omega at corner frequency. Or omega CF, you can say omega CF is what? Corner frequency. Okay, omega CF is, let me define omega CF here anywhere at the starting, because else you'll get confused. So omega CF is corner frequency. Okay, in this case the corner frequency is what? 1 by tau. In this case the corner frequency is 1 by tau. So they, both of them are same thing. If I write 1 by tau or omega CF, they are talking about the same thing. So now the actual value of phase, what is it? So let me put this in equation. Minus n tan inverse 1 by tau into tau itself. It was tan inverse omega tau, right? It was tan inverse omega tau. So simply in place of omega I put 1 by tau. So this becomes minus n. What is tan inverse 1? So this is tan inverse, actually, sorry. It is simply 1. It is simply 45 degrees. So it becomes minus 45 degree minus 45 n. Okay, I hope you understand how this negative sign came. This negative sign came as this was in the denominator. So calculating phase I won't teach you, but we have learned this previously. So this is in the denominator, that's why the negative sign came along with the tan inverse. If this was in the numerator, then obviously no negative sign would have come, only the n or m term would have come. If I had m zeros, it will be m tan inverse omega term. Okay, so as we can see, this minus 45 n degrees, and from here the approximate value of angle of g of j omega at omega equals to omega cf equals to what? Minus 45 n equals to minus 45 degree n. Okay, so this is the approximate value and this is the actual value. So what is the error? Error is 0. So error corner frequency is 0. So this is error. I should write here error in, let me Bode gain plot, and here the error will be simply 0 because both of them are telling the same thing. So we are mainly interested in the corner frequency. Bode phase plot. Okay, so this is the error in Bode phase plot and Bode gain plot. This is like the short notes I've given you, like just the definition, that if you have n real and repeated poles, then my error in dBs will be minus cn. Obviously in phase it is 0, that's why we don't write it, it's not relevant to us. Okay, and if you have m real and repeated zeros, then the error in dBs will be plus 3 times m. Okay, here we have got this answer, minus 3n for poles. Obviously for zeros it will be inverse, you prove it for yourself, I don't want to waste much time. It will be plus 3m. What is important thing, even like error in gain plot is always even symmetric about the corner frequency. Why? Because initially the error is increasing, then it reached the corner frequency, there the error become maximum, then the error reduce. So it is error in gain plot is always even symmetric about corner frequency. Error in phase plot is always odd symmetric about corner frequency. So error in phase plot is always odd symmetric. Because why is it odd symmetric? Because suddenly it increases, then it starts to reduce. Why? Because here the effect of slope comes like 10 times before the corner frequency. Now this approximate plot is trying to catch up with this actual plot. That's why the error starts reducing. Here the error starts increasing because this is doing nothing, then it starts reducing, and it reduces to really 0 here at the corner frequency. Then this approximate plot catches too much, so that's why it goes downwards, and here the error is positive again. Here the error is positive again, it becomes 0 after the 10 times after the corner frequency, because this one also goes to minus 90n. Okay, this one also goes to minus 90n. So this is about the error. Okay, so that's why this is odd symmetric about the corner frequency. Now let's start up with our relative stability parameters. Nothing to define here, we already know everything. What is gain crossover frequency? Gain crossover frequency is the frequency at which the gain of my OL tape becomes 1. But all these are defined for unity negative feedback system. Do remember, unity negative feedback system. Defined for unity, I tell this 100 times, unity negative feedback system. Now if they don't mention anything, or they are telling you to find it anyways, obviously you will find it, but generally this is the thing, that it is defined for unity negative feedback system. What is gain crossover frequency? The frequency at which the magnitude of my voltage becomes 1. Okay. What is the phase crossover frequency? The frequency at which the phase of my OL tape becomes minus 180. Okay, it crosses the negative real axis. What is the gain margin? Gain margin is the reciprocal of magnitude of my OLTF at the phase crossover frequency. Okay, magnitude of the OLTF, reciprocal of the magnitude of the OLTF at the phase crossover frequency. This is the additional amount, of margin. Yeah, this is the additional amount of margin left for it to become unstable. Like we learned this in gain margin, right? What amount of margin is left until it gets to the critical point, -1, point. Like gain, in terms of gain, what amount of margin is left. So this is this case. Our gain margin is defined like this: kg equals to 1 by magnitude of omega gp into hgp, like where p is phase crossover frequency, omega p is phase crossover frequency. And if you write in dBs, what does this happen? Obviously this is 1 upon something. Obviously log of 1 is 0, log of this upon, like, is denominator. Obviously what is this power? Power is negative, right? Like if you write this here, this magnitude, this power, this power is negative. So obviously this -1 will come in front. Okay, with this 20 dB, like we're converting to dB, so -1 will come in front. So this will be minus of log of this. Why I'm explaining you all this? Because in the Bode gain plot, we'll see this gain. Okay, in dBs we'll see this gain. We just have to multiply a -1 with this to find the gain margin. Okay, don't just simply write that one, because that is not the gain margin. That is the gain of my OLTF at phase crossover frequency. That is not the gain margin. Gain margin is the inverse of the gain, but it is written in dBs over there, so we don't take the inverse, we just multiply a -1. Okay, because it is the inverse in decimal format, decimal scale, but in dB scale we will multiply minus, because inverse in decimal scale, absolute scale, obviously means I multiply by -1 in log scale. Okay, I hope you know, right? Basic of log we have done in the first lecture itself. Okay, so yeah, that's why we multiply a -1 in that plot. Okay, now this is about the gain margin. What is the phase margin? Phase margin is the additional amount of phase lag, remember lag, that needs to be added to the phase of the system at omega equals to omega g to bring the system at the verge of instability. Basically, how much phase is left for it to cut the negative real axis. So it was like, which is at the gain crossover frequency. So at gain crossover frequency, what is my phase, and what is the phase difference between those two? So the simple formula was 180 plus angle of my OLTF at phase crossover frequency. Not explaining much, but what are the important points to note here is that this gain margin is not a function of phase crossover frequency. Okay, told it wrong. The gain margin is not a function of gain crossover frequency. Do remember that, because with gain you might get confused. Like this is also known as GM. But don't get confused. My GM, as gain is the name of this one, gain margin is the name. It is not a function of the gain crossover frequency. It is only a function of phase crossover frequency. And similarly for here, my phase margin, this is known as phase margin. My phase margin is not a function of phase crossover frequency. It is a function of gain crossover frequency. Students get confused in this. Please don't be confused in this. Okay, please. So like, you don't find the phase crossover frequency and then find the phase margin. So shouldn't be confused in this. Okay, this we have learned in detailed manner in the polar plot chapter. So like, just wanted to give you a quick refresher about the phase margin, gain crossover frequency, and phase crossover frequency. Let's solve a question. So this is a GATE 2014 easy question. Here the phase margin in degrees of g of s equals to 10 upon this. Okay, like OLTF is given. Calculate using the Bode asymptotic phase plot. Like we have to calculate the phase margin in degrees for this simple OLTF. So nothing is set. We'll assume unity negative feedback system. Nothing is set. Okay. So we have to calculate the phase margin. How to calculate the phase margin? For phase margin, first I have to know where does it hit. Where does the magnitude of this function is 1? At which location magnitude of the function is 1? So now after I find the frequency, then the frequency I will go to the Bode phase plot, and there I will identify what is the phase at that frequency, and with that phase I will add plus 180, and that will be my phase margin. So this is the simple procedure that we'll follow. So this has told us with Bode plots what to do. We don't have to do approximate analysis. If we had to do approximate analysis, how would have done? We would have simply equated the magnitude of this one equals to 1, which would have been difficult for us. Like we have to solve a third order equation. We have to solve a third order equation. I hope you remember it. In polar plots, we solved higher order equations and solving them was difficult. That's why Bode plot helps to find this relative stability parameter of higher order systems with with faster without taking much time. So this is one advantage of Bode plot. So help us find relative stability parameters of higher order systems with less calculation than conventional method. Less calculation than conventional method. Conventional was simply equate the magnitude equals to 0. Sorry, not 0, equals to 1. But obviously here this is conditional. Why? Because here approximation is involved. So our answer won't be totally exact. This is conditional as approximation is involved. But we engineers, that's the job of our engineers, to make good approximation so that our resources, minimum resources are used to find the value, and still we get a good enough approximation to use that in real life scenario. That is the major work of engineers, right? So like this computer, all these things that we use, it should, like, we should get a good approximation. It should not use too much of resources, and still it should give us the output. That is the work of engineers. Okay, so as conditional as approximate this is approximate analysis. We don't get exact values. Okay, we don't get exact values. So this is the conditional thing. So now let's solve the question. So first what we'll do, we'll draw the Bode gain plot. So gain plot we can draw just in matter of seconds. G omega and omega, and this is in log scale, to remember. Now here they've given us the transfer function. Okay, and for this, from where I will start from here. Like I will mark the corner frequencies, 0.1, 1 and 10, and obviously I will convert this into general time constant format, because this is not in general time constant format. So if I convert this into general time constant format, what do I see? This is 10 10.1 s by 0.1 plus 1 s plus 1 and this is 10 times s by 10 plus 1. Okay, so this is 10 times 0.1, which is 1, and this is 10 again. So overall this is 10 only. Okay, so here one thing I observe is that I have a 0.1 as corner frequency, so obviously I will not approximate from 0.1. What I'll do, I will approximate from 0.001. Anyways, I can see that DC gain is 10, so I will start from 20 dBs anyways, but still we can't show 0 omega is 0 here. So what I will do, I will start from 0.001. Okay, if we approximate from 0.01, then obviously what will happen, you can, like, while calculating the magnitude, you can ignore this, okay, then only 10 will remain, and 20 log base 10 is 20 dBs. So we'll start from 20. Okay, it will be constant here until 0.1. Then what do we encounter? We encounter obviously poles. At each corner frequency we encounter poles. So at each corner frequency my slope will reduce by minus 20 dB per decade. Here my slope is 0 dB per decade. It becomes minus 20 dB per decade until 1. Then it becomes minus 40 dB per decade. Then after 10 it becomes minus 60 dB per decade. This is 0 dB per decade. And this is minus 20 dB per decade. This is minus 40 dB per decade. This is minus 60 dB per decade. Okay, so these are the slopes. Now what we are interested in, to find the gain crossover frequency. So gain crossover frequency is the frequency at which my gain is 1, or in dB scale it is 0. So here I observe it is reducing by minus 20 dB per decade scale. So for 1 decade it is reducing by 20 dBs. So it was 20 dBs here. So if it reduced by 20 dBs, it becomes 0 dBs. So if I travel 1 decade from 0.1, I will reach 0 dBs. So obviously this is my gain crossover frequency. This is my omega GC. Okay, so omega GC is 1. So this is what we understood. But here, that is the main thing, that here what is the error at the corner frequency? What is the error? As the slope is only 20 dBs, okay, 20 dBs slope is changing, like one pole we get, the error will be 3 dBs. So like the maximum error that we'll get, obviously this is error, because if you put omega equals to 1 in this, the magnitude expression, what you will get? You will get 10 by root 2, 10 by root 2, this is omega 2, yeah, this is just hold on a second, this is sorry, yeah, this is 10 by not 10 by root 2, 1 by root 2, because this one becomes 10, this magnitude becomes 10, and this magnitude becomes 2. So 10 times 2 under root 10 by under root 20. Okay, so let's do this anyways. So actual value, magnitude of g omega at omega equals to 1. Okay, which where from the Bode gain plot it says it is the gain crossover frequency, as the gain is 1 at that frequency. Let's see if it really is 1. So what is this? This is 10. This is under root 1 divided by 0.1 whole square plus 1. Okay, simple, I'm doing it simple, like omega by 0.1, omega and omega by 10, and this is 1 square plus 1 square, and like this is also square, and this is 10 times 1 square plus 1 square. Okay, is this 10? No, yeah, this is okay, fine. Is this correct? No, this is by 10, right? This is by, no, sorry, this is by 10, not into 10, this is by 10. 1 by 10 whole square plus 1 square. Okay, so what is happening basically, so we can ignore this because 1 by 10 is 0.1, 0.1 whole square is 0.01, so simply 1 will remain only. So like, let me write this here, else it will be very much messy. Just doing this in rough. Okay, so obviously we can ignore this, only this and this will remain because this is 10 square, like 1 by 0.1 is 10, 10 square is 100, so 100 times 2, like I'm ignoring this one now, ignoring this one here and ignoring this one here. So obviously what I will get, 10 upon under root 2 times 10, so it becomes sorry, this is also 10 square, actually this is under 2 times 100, so this is 1 by root 2, which is 0.707. So in dBs, if we calculate this one, this will be minus 3 dB. Okay, in dBs this will be minus 3. Okay, so here we observe that, yeah, it is giving me error, but that is fine, okay, because we want to approximate it, we don't need the exact values sometimes, because approximation also is good enough if we are using very less resource. Because if we try to equate this, like if you equate this equation with 0, like magnitude function with sorry, not 0, equals to 1, it will consume more time. Okay, that is the reason. So that is done. Now let's do the phase plot. So the phase plot will be a bit like time consuming. Okay, so yeah, don't worry, it the question is taking me time because I'm explaining you every aspect of this. Okay, it will not take you much time, but it will take time, 2 minutes it will take, because the Bode phase plot is time consuming, but not as much this one, because I'm explaining you everything, all the concepts, that's why it is taking me so much time. So phase plot, I will again copy the table. Okay, that phase table, where is the table, it's too much, here. Here is the table, right? So I will just paste the table here. Sorry for the burping. Yeah, now we only have poles, so I will only write poles here. And what are my different thresholds? One is from one is at omega equals to 0.1 and 1 and 10. So the thresholds will change, 0.1, 1 and 10. So here all of them are poles. So this is omega p1, 0.1, 10. This is 1 to 100. Okay, and okay, sorry, this is 0.01. This is 0.01. Actually, that missed bit away. 0.01 to 1. Then I have 0.12, because this is the corner frequency, like 1. So this is 10 times before and 10 times after. And this is what this is. This is like 10 times before, so it is 1 to 100. The corner frequency here is 10. So I hope you are understanding the ranges, right? Corner frequency omega p1 is 0.1, this is 1, and this is 10. So 10 times before and 10 times after of all of this. Now what are the ranges for here? The ranges I will delete. Okay, I will just delete the ranges. The ranges will change. So here what is happening here? So first obviously we'll check for less than 0.001. So 0.001, there will be nothing. Then what is happening after that? What is the next least value I am getting? Next least value is 0.1. So I'm moving every decade. If you see 0.1, then 1, then 10, then 100. So I will just write the ranges accordingly. That. So this will be 0.1, this will be 1, this will be 1, 10, 10 and 100. Okay, and this will be the last range will be omega greater than 100. Okay, so like what is happening before, like 0.001, nothing is there, so obviously this will be 0. This is fine. Now between 0.1 to 1, between 0.1, sorry, this is between, sorry, one thing I missed out. This will be 0.01 to 0.1. 0.01 to 0.1. So this is 0.01 to 0.1. What does this mean? This means that 0.01 is active here and 0.1 is here. So this pole hasn't even come to effect, and this was also not come to effect. Only effect due to this one will be seen. So what is the effect? A slope of minus 45 degree per decade. So here I will get a minus 45 degree per decade due to omega p1. Fine. Next, what is happening? Just let me bring it this down. Next, from 0.1 to 1, 0.1 to 1, so this is omega p1 is still active, and 0.1, so this p2 becomes active, but this p3 doesn't get active because this is less than 1. So I am getting two poles active, so obviously overall slope will be minus 90 degree per decade. So this will be minus 90 degree per decade, and this is due to omega p1 and omega p2. Okay, then what is happening here, like from 1, so after 1 this pole becomes inactive. Okay, the effect due to this pole becomes inactive because this is only active between this range. So after 1 this is active still, and this is still active within the range. So still my slope will be same, minus 90 only, but this time the effects due to the poles like will change. Like this time which poles will be active? Omega p2 and omega p3 instead of omega p1 and omega p2. Now after this what is happening? So after this now, where were we were here, right? So let me just delete all this because this is being confusing. After this, after 10, so after 10 this omega p2 also becomes inactive. This is anyways inactive, so both of the poles become inactive, only this pole is active. So only one slope will be there of minus 45 degree per decade due to this is, yeah. Then after this what is happening? After this omega is greater than 100. So if omega is greater than 100, what does that mean? Omega is greater than 100, that means none of them are contributing. So again the slope will be 0. Okay, slope will be 0. Slope will become 0. Okay, so let's just plot the this Bode phase plot. Okay, from there we'll compare. So let's just plot the Bode phase plot. This is angle of g omega. Okay, and let's start from 0.01 itself, 0.01, or let's start from 0.001 actually, because like 01 is already occupied here. 01 is already occupied here. So 0.001 will start. So initially starting from 0 degree, because this value of this this is positive, 0 degree. So initially we start from 0 degree. Let me mark the corner points also. So here let me mark as 0.01, then 0.1, then 1, then 10, then 100. Okay, so let's now go to this. So this is 0, Okay, then what is happening? Then after 0.01, what is happening? After 0.01, my slope is minus 45 degree per decade. So it reduces to minus 45 degree per decade. Okay, I will not move it like this. Move it like this. After 0.1, what is happening? After 0.1, what is happening? After 0.1, it is the slope is going to minus 90 degree per decade. So it further reduced to minus further minus 45. So slope gone to minus 90 degrees per decade. And after 1 also, like slope is still same, minus 90 per decade. So we can extend this. Okay, I will just extend this like this. And after 10, what is happening? Slope is again going to minus 45 degree per decade. So we can do it like this. And I think I need to keep this more up. Okay. Now after 100, obviously the slope becomes 0. So like here, let me write the slope at each point. So this is 0 degree per decade. This is 45 minus 45 degree per decade. This is minus 90 degree per decade. And this is again minus 45 degree per decade. And this is 0 degree per decade. Okay. So what about the corner frequencies? Here the corner frequencies is, so what I am interested in is to find the value of phase at this 1 radian per second. So how to find the value of phase? So we can easily find it out because everything is moving in decade scale. So generally they give you either everything will move in octave scale or decade scale. Here all the corner frequencies are moving in decade scale. So I will solve in decade only. If this was in octave, then I have to solve in octave scale. Okay. So I have to find the phase at this 1 radian per second, and I'll just add 180 with it. Then I will get my phase margin. So this value is 0 degrees. Okay. And after this 0.1, I am moving 1 decade and the slope is minus 45 degree per decade. So obviously overall how much I moved? I moved minus 45. Minus 45. As what does this slope tell me? You move 1 decade and you have to move down by 45 degrees because this is moving in minus 45 degree per decade. Now after this, what is happening? After this, we have a slope of minus 90 degree per decade, and I move 1 decade at 1 and the slope is minus 90 degree per decade. So 1 decade I move and my slope is minus 90 degree per decade. What does this mean? You move 1 decade and you move down by 90 degrees. So currently my value is minus 45. I will move down by 90 degrees. So this will be minus 135 degrees. Like another decade, if I move, the slope is same. So I will again move down by 90 degrees. So this will be, obviously we have found out our value, but still I am continuing. This will be minus 225. Again, what is this telling? This is telling that my slope is minus 45 degree per decade and I am moving 1 decade. So 1 decade you move down by 45 degrees. So this becomes, why am I continuing? I will just explain you. Let me finish. This becomes minus 270. Okay. So this becomes minus 270 and we stop there. So like this, you can cross verify whether your phase plot was correct or not. Because as omega tends to infinity, what should be your phase? As omega tends to infinity, we have 3 poles. So all of them will contribute. Each of them will contribute minus 90, minus 90, minus 90. Overall, minus 270. So yes, at the end, I am reaching minus 270. So my phase plot is correct only. Or you can use that formula, minus 90 into n minus m, where n is the number of poles and m is the number of zeros. So minus 90 into n is 3, m is 0. So minus 90 to 3 is minus 270. Here also you can cross verify the slope. What is the slope at the end? Minus 60 dB per decade. What was that formula? Minus 20 into n minus m. Minus 20 into 3 minus 0, which is minus 20 into 3, which is 60 dB per decade. So here, that this is also satisfying. So you can cross verify like this, that yes, my Bode magnitude was correct and my Bode phase plot was correct. Like this will help you in test series or something. Like when you are making a silly mistake, you will be notified that yes, I'm making some silly mistake in making this plot or something. I have to again redo it. Else you will answer the question and you will get negative marks. Okay, just to save you from that silly mistake. All these cross verification techniques needs to present, right, so that you won't make any silly mistake. So yeah, we have got our angle. So angle of g of j omega at omega equals to omega gc equals to simply minus 135 degree. So phase margin equals to 180 plus minus 135 degree equals to 45 degree. Now if you have enough time, what I want to do is calculate the exact value of phase margin and see how much are they differing. How much are they differing? So from there you will understand whether this was a good approximation or not, because obviously this is approximation. 45 degrees is approximate. 45 degrees is the answer here. 45 degrees is the answer here. Okay, but this won't be exactly like if they would have told us to find the phase margin exactly, this won't be the answer, as they have told us to calculate the phase margin using the asymptotic Bode plot. So that's why 45 degrees came. Okay, so yeah, that is one thing. Now let's come to the steady state error. You don't have to think much about steady state error. Just like this is only valid if the Bode plot of the OLTF is given. Like Bode plot of the OLTF is given and the OLTF is of unity negative feedback system. OLTF given for a unity negative feedback system. Only valid if the Bode plot is given for a unity negative feedback system. This is the new unity negative feedback system. And what is the error here? Like if you recall everything correctly, what was the error? Like I know it has been months since we studied the steady state error. It was E of t equals to R of t minus C of t, okay, in time domain expression. Now these are different coefficients which I also had to remember, but still we have to, because sometimes question may come from this. But you can find the error using the basics only. Just you calculate the Laplace domain expression of this one and then use the final value theorem and you got your error. Okay, don't need to remember all this jargon, but still we have to sometimes, because question may come and they may ask you, tell me the positional error coefficient of this OLTF. Then obviously you have to know the term position error coefficient. First, this is valid for type 0 system, and from the graph we will understand what is the position error coefficient. This is given, OLTF is given, and my Kp is the position error coefficient. And what is it defined? How is it defined? Kp is my position error coefficient. Kp, let me write positional. So it is equals to limit as s tends to 0 g of s, basically the DC gain of my OLTF. This is also known as DC gain of my OLTF. Okay, this is also known as DC gain of OLTF. So here, what is the corner frequency? Corner frequency is 1 by tau. 1 by tau. Okay, so at low frequencies, what is the DC gain? So let's say this is 0.1 by tau. So this is becoming a bit congested. This is 0.1 by tau. At lower frequencies, obviously, if you calculate the magnitude, this will be ignored. The magnitude will be k, and in dBs it will be 20 log k. Okay, this will 20 log k, and here the slope will be minus 20 dB per decade. Like this is just single pole. Now can you tell me the positional error coefficient from here? The positional error coefficient is simply what? Simply the DC gain, which is k. So here the positional error coefficient will be, like from Bode plot, it is 20 log k, and you have to convert it into normal scale. So here it is k, and k you can find from the Bode plot. If you want to find the positional error coefficient, you find from here. Okay, the initial slope. So if the initial slope is 0, remember, if the initial slope is 0, then only you can find the positional error coefficient, else you won't be able to find. Okay, if the initial slope is 0, then only you can find the position error coefficient. So I should write this down, that if initial slope is 0, then we can find Kp. Okay, else we won't be able to find, because Kp is only valid for a type 0 system. Here it is a type 0 system. Kp is only valid for type 0 system. Okay, now what was the error formula? Like, I won't recommend you to remember that, but just remember that what is Kp and K. Error we can define it by basics. Through basics we will derive it. Okay, we'll do one question and through basics I will do it. So initial slope is this. So my Kp will be simply this. Okay, so 20 log K equals to 20 log Kp. Okay, now what is my velocity error coefficient? What is my velocity error coefficient? It is valid for type 1 system, and if the system is type 1, obviously initial slope will be minus 20 dB per decade. Initial slope will be minus 20 dB per decade. Okay, initial slope will be minus 20 dB per decade. Then, like, what is happening? Like, let's assume that my tau 1 is greater than tau 2. So at this point, like, we have got two corner frequencies. This is 1 by tau 1, this is 1 by tau 2. Okay, and this is minus 40 dB per decade. Okay, and this is minus 60 dB per decade. But what is interesting here? Interesting here is, I will tell you, but first let me define the velocity error coefficient. What was my velocity error coefficient? My Kv. Like, if you want to remember, like, I won't recommend you. I solve from basics itself. But here, what will be my steady state error for the positional error coefficient? Steady state error will be A upon 1 plus Kp. Okay, only if my input is R of S equals to A upon S. Okay, so only for this condition my error will be this, else my error will be something else. Just remember this. Okay, so yeah, this is my, or I can write in brackets, this is my input. This is my input. So this is my input, the error is this. Now let's do it for here. So what is my Kv here? What is my Kv here? Everything is recording, right? I just sometimes get scared that everything is getting recorded or not. Everything is getting recorded. What is Kv? Kv is the velocity error coefficient. Like, we have already done this. Velocity error coefficient. And what is it defined as? It is defined like something like this. Limit as s tends to 0, s g of s equals to what? Equals to, here if I do limit as s tends to 0, s g of s gets cancelled. So now I can put s equals to 0 here. So this will get cancelled. I will be remained with only k. So this is equals to Kv, and this is not equals to dc gain. Not equals to dc gain, because dc gain is infinite for this, dc gain is infinite for this. Not equals to dc gain. So people get misconception by this, that this is dc gain. No, this is not the dc gain. This is not the dc gain. Okay, dc gain is infinite for this. So this goes to, like, this goes to k, and k is equals to Kv itself. Okay, now how to find the value of k? Now if you remember, we have already solved question like this, that if I extend the initial line, and the point where it cuts the 0 dB axis, from there we can relate the value of k. I hope you remember. So I will extend this initial line. Okay, and here it cuts. Here what will be value? This is what? This is omega gc, and this is equals to k itself. Now, like, this actually the formula is k raised to power 1 by n. Like, it isn't the formula, we derived from the basics, but still if you want to memorize the formula, it was k raised to power 1 by n. Here n is 1 because type 1 system, only one pole at the origin. So here my omega gc will be k itself. Omega gc will be k itself. Okay, so yeah, this is the case. Now here also I have written value of omega where the initial line cuts the 0 dB axis is equals to Kv. okay, is equals to kV itself. So obviously, uh, how is it equals to kV? How is it equals to kV? Like from here you understand, but let me give you intuition. Like we have already done this, still let me give you intuition. So at low frequency region, how this will behave, how this will behave at low frequency region. This is very low, this is very low, s tau is very low, s tau 1 is very low, s tau 2 is very low. So 1 will dominate, so this one I can ignore, I'll be remained with only k by s. So at low frequency region, this is k by s. So my g by g dash or g of s can be written as k by s. In low frequency it can be written as like this. Now what is happening after this? Now what is the magnitude? Magnitude is g of j omega equals to k by omega. Now at unity gain frequency, my k is equals to omega gc equals to 1 at omega equals to omega gc. So k equals to omega gc. So from here you can understand that we're getting the same formula as I told you here. And if you know the k, obviously k is equals to kv. K is equals to kv. Okay. And what is the steady state error formula? I don't recommend remembering this, but still if you want to, the steady state error formula for this one is a by kv. A by kv. The steady state error for this a by kv. Now it is a by kv for what? Very important. For what? For input or r of s, r of t. Did I write r of s there? Yes. Okay, fine. Or you can write like unit step input, like r of t equals to a u of t. You can write it like this. No need to write like that. For r of t equals to t u of t. Okay. So this is what my like input is. For this input only, the steady state function will be something like this. This is not only a, this is a t of u of t. So a t of, okay. So yeah, this is the coefficient. I won't derive it, we don't have time. I will derive it in the steady state error part. So now the acceleration error coefficient. So acceleration error coefficient is same only for type 2 system. I will go a bit faster right now. So acceleration error coefficient ka error coefficient okay is this. So this is defined as limit as s tends to 0 s square g of s, s square g of s, which is equals to k itself, because if you multiply s square here, so now if you put s equals 0, this one we can ignore, and like this will be remain k by 1 times 1. So this is k itself. So it is equals to ka itself. But remember, this is not the dc gain, not equals to dc gain of OLTF. This is not a dc gain, remember this. Okay, this is value for type 2 system. So obviously we have a type 2 system here. So what is the slope here? The slope here is type 2 as, so this will be minus 40 dB per decade. This is again like we are getting another corner like a pole here. So this is 1 by tau 1 by tau 2. Okay, this is minus 60 dB per decade, minus 80 dB per decade. Okay, so the slopes are like this. So what we are interested in, this k value. We have to find this k value. And what was the relation? Remember, so now if I extend this line, if I just extend this line, the intersection of the 0 dB axis, okay, what will this equal to? So this will be, let me take another color, this will be omega gc omega gc square will be equals to k itself, or the other way around, k was equals to omega gc was equals to k raised to power 1 by n or 1 by 2, but here omega gc square equals to k. This also you can write. Okay, so how does this come up? I have explained this again. I will explain this, but first let's read this. The same thing is like written over here, that value of omega where the initial line cuts the 0 degree axis is equals to the square root of k. So what, like square root of k, yeah, like what is the value of the omega then? Omega equals to omega gc equals to under root k, because k is equals to k under root k. Okay, so that is what is written over here, don't worry. Now how to approximate this? So like again I will use the same thing for low frequency region. What is happening, my g of s I can write. Obviously I will ignore all this because 1 plus very low value, ignore 1 plus very low value, ignore. So only k by s square. So I am remained with k by s square. Okay, only k by s square. Now let's find the magnitude of this. So if I write the magnitude, it is g of j omega equals to k by omega square. Okay, which is equals to 1 itself, at omega equals to omega gc. So which is equals to 1 itself. So now what do you do? So this is k will be equals to omega gc whole square, right? So ka will be equals to omega gc whole square. Okay, so this is how we write the expression there. Okay, so what is my steady state error? Like the formula, obviously I won't recommend you remembering this, but still I am writing. What is my steady state error? So my steady state error is simply a by k for what? For a input r of t for input r of t as a by 2 into t square u of t into t square u of t. Okay, so this is my steady state error for this like acceleration error coefficient. Now like I have given you the summary. Okay, how to find the coefficients. Only this for the coefficient, don't need to remember the error, steady state error. You can do it by the basics from the block diagram itself. So for like if the initial slope is 0 degree per decade, 0 dB per decade, then you know this is a type 0 system, and for type 0 only positional error coefficient will exist, and the error coefficient will be equal to this, the initial amplitude. Okay, 20 log base and kp. Now the error stage error formula is this, I am not mentioning. Now if the initial slope is minus 20 dB per decade, then the type is type 1 system. Like from this slope we understand this type 1 system, and the kv, the velocity error coefficient, will be the 0 dB axis intersection. Wherever it intersects with the 0 dB axis, that value will be equals to kv itself. Okay, the frequency. Okay, here also this is same frequency. Okay, I hope you like understand that what do I mean by frequency. Gain crossover frequency basically. Okay, frequency of the 0 dB axis intersection, wherever it intersects, the frequency at which it intersects, that will be equal to my velocity error coefficient, and the input is at of ut, ramp input. For that my error will be a kv. Okay, for that only my error will be this. Okay, for any other input the error will be not this. Just remember this. That's why I don't recommend remembering this. Someday they will change the input, then remembering all this will be just a waste. Okay, that's why. Then if my input is initial slope is minus 40 dB per decade, then type is 2, then this acceleration error coefficient, the under root of acceleration error coefficient is equals to the frequency at which it intersects the 0 dB axis, and the input is like the parabolic, then the error is like this. Okay, so this is one question. Okay, this is one question. So what I will do is I will give you this as homework. This is a straight error question. You can solve it using any method, that coefficient method or your simple method. And in the next lecture, I will start with this question and we'll learn about Bode plots for second order systems. Okay, and we'll do a few questions on the second order systems. And another lecture we'll do all the questions from Bode plot. Okay, and then we'll wrap up the Bode plot chapter. So yeah, thank you for watching, and I will see you in the next lecture.